So in the previous videos, we have discussed both vertical asymptotes and horizontal asymptotes. Here we're going to discuss oblique asymptotes. So what is an oblique asymptote? Sometimes a line that's neither vertical nor horizontal is an asymptote. Such a line is called an oblique asymptote or a slant asymptote. Oblique asymptotes occur when the degree of the numerator is 1 greater than the degree of the denominator. So previously we've seen that if the degree of the numerator and the denominator are the same, we'll have a horizontal asymptote. If the degree of the numerator is smaller than the degree of the denominator, we'll have a horizontal asymptote. So if the degree of the numerator is larger than the degree of the denominator, we will not have a horizontal asymptote, but we may have an oblique asymptote. So again, if the degree of the numerator is 1 greater than the degree of the denominator, then we'll get an oblique asymptote, which will be a slanted line that the graph gets closer and closer to instead of a horizontal line. So let's take a look at an example. So in this example, we want to determine the oblique asymptote of the graph of the rational function f of x equals 5x cubed minus x squared plus x minus 1 over x squared minus x plus 2. So notice that this graph will have an oblique asymptote because the degree of the numerator is 3, the degree of the denominator is 2, so the degree of the numerator is 1 larger than the degree of the denominator. So that's how I know for sure that I'm going to have an oblique asymptote. So we want to figure out what that oblique asymptote is going to be. So to determine what the oblique asymptote is going to be, we're going to divide the numerator by the denominator, and whatever the quotient is will give us the oblique asymptote. So we're going to take 5x cubed minus x squared plus x minus 1, and we're going to divide that by x squared minus x plus 2, and to do that we're going to use polynomial long division, which we've done several times before. So I look at the x squared and I look at the 5x cubed. What would I multiply x squared by to get 5x cubed? And the answer is 5x. So if I multiply back, 5x times x squared is going to be 5x cubed. 5x times minus x is minus 5x squared. 5x times plus 2 is plus 10x. If I subtract, I have to distribute the subtraction, so this is going to become minus, this is going to become plus, this is going to become minus. So 5x cubed minus 5x cubed goes away. Negative x squared plus 5x squared is going to be 4x squared. Plus x minus 10x is minus 9x, and I'm going to drop down the minus 1. Looking at the x squared and the 4x squared, what do I multiply x squared by to get 4x squared? The answer is 4. So multiplying back, 4 times x squared is 4x squared. 4 times minus x is minus 4x. 4 times 2 is 8. Distribute the subtraction. This becomes minus, this becomes plus, this becomes minus. 4x squared minus 4x squared goes away. Minus 9x plus 4x is minus 5x. Minus 1 minus 8 is minus 9. This is the remainder. So our oblique asymptote is going to be the line y equals 5x plus 4. The quotient gives us the oblique asymptote. We do not worry about the remainder for the oblique asymptote. So our oblique asymptote is the line y equals 5x plus 4. Again, the 5x plus 4 comes from this. Like with the vertical and horizontal asymptotes, we must write the oblique asymptote as a line, as an equation. So you have to have the y equals. If you say that the oblique asymptote is 5x plus 4, that's not really correct because 5x plus 4 is an expression, not an equation. not a line. So you need the y equals to make that be a line. Now, let's take a look at this equation on our calculator. So if we look at our function, 5x cubed minus x squared plus x minus 1, that's all in parentheses, divided by parenthesis x squared minus x plus 2. And I'm going to also go ahead and draw in our oblique asymptote, y equals 5x plus 4. Now I'm going to try a zoom 6, but I'm not sure that's going to give me a decent looking picture. That's not terrible. So we can see that the blue graph here, that is our rational function. And so the blue graph is getting closer and closer to our oblique asymptote as x goes to infinity and as x goes to negative infinity. So we can see that our graph is approaching that. If I look a little higher and a little lower, so if I change my window to view maybe like from negative 20 to 20, that may show that even a little more clearly. And it does. So we can kind of see that the graph, it's actually crossing the oblique asymptote and then turning back and getting closer. And then the same over here, it's not crossing, but it's just curving and getting closer and closer to that oblique asymptote. So this is sort of the idea of what's happening with an oblique asymptote. The graph's approaching the slanted line rather than a horizontal line. So let's summarize what we've learned so far about asymptotes. So occurrences of lines as asymptotes of rational functions. So for a rational function, f of x equals p of x over q of x, where p of x and q of x have no common factors other than constants, vertical asymptotes are going to occur at any x values that make the denominator 0. The x-axis is the horizontal asymptote when the degree of the numerator is less than the degree of the denominator. A horizontal asymptote other than the x-axis occurs when the numerator and the denominator have the same degree. And remember that horizontal asymptote is going to be the leading coefficient of the numerator divided by the leading coefficient of the denominator. An oblique asymptote occurs when the degree of the numerator is 1 greater than the degree of the denominator. So again, like in the previous example, the degree of the numerator was 3, the degree of the denominator was 2. So the fact that the numerator's degree was 1 more than the denominator's degree meant we had an oblique asymptote. There can only be one horizontal asymptote or one oblique asymptote, never both. So if we're talking about a rational function, you will have a horizontal asymptote or an oblique asymptote or neither. You will have one or the other or neither. You cannot have two horizontal asymptotes. You cannot have two oblique asymptotes. You cannot have both. You'll have one or the other, but not both. And you may not have either. If the degree of the numerator is more than 1 greater than the degree of the denominator, then you will not have an oblique asymptote. An asymptote is not part of the graph of the function. So again, we draw those as dotted lines for reference, but they're not really part of the graph. They're just there for reference. Crossing an asymptote. The graph of a rational function never crosses a vertical asymptote. That is impossible. A rational function cannot cross a vertical asymptote. The graph of a rational function might cross a horizontal asymptote, but it doesn't have to do so. So it could maybe cross a horizontal asymptote, but it doesn't have to. And the same for an oblique asymptote. It might cross an oblique asymptote, but it doesn't necessarily do it. So for example, let's say I have a vertical asymptote right here, and let's say I have a horizontal asymptote right here. It's possible that the graph could say maybe come up, go across the horizontal asymptote, and then curve back and become asymptotic like this. But it cannot cross the vertical asymptote. So it would do this, maybe come up, cross, and then get asymptotic. That's possible, but it doesn't have to. It may also just come up and be asymptotic from the underneath side. It doesn't have to cross a horizontal asymptote, but it could. What it cannot do is it's never going to cross when it's going out towards infinity. It's always going to cross up here. And then the same kind of thing would happen, or could happen, with an oblique asymptote. So if I have, say, a vertical asymptote like right here, and then I have an oblique asymptote like here, it's possible that the graph could, say, come up, cross, and then get asymptotic. So it's possible that it could do something like this, or it's possible that the graph could come up and just get asymptotic to that oblique asymptote like that. So again, the point is a rational function's graph's never going to cross a vertical asymptote. It might cross a horizontal asymptote or an oblique asymptote, but it doesn't have to.